Now that we have a rough understanding of what is capacitor, so let's bring in a bit of maths and a bit more formal discussion of the idea of capacitance. Okay, so capacitance, it's a new physical quantity that we introduce to describe the ability of a capacitor to store energy of charge. So if you have greater ability to store energy or charge, or you can say you store more energy or you store more charge, then you have greater capacitance. If you have less ability to, you're less able to store energy or less able to store charge, or you can say you store less energy or you store less charge, then in that case you can say you have a smaller capacitance value. Okay, so the definition of capacitance is the ratio of the charge on each conductor to the potential difference between the conductors. Okay, so to understand this ratio, I need to draw a bit of a diagram. Draw a bit of diagram to understand the idea. Okay, so we can think of a situation like this. Let's say we have a capacitor. So a capacitor initially it's neutral. Okay, so you can think of it something like this. Okay, so the amount of positive charge and amount of negative charge is equal on each place. Okay, in this case I represent it by 3 positive charge and 3 negative charge on each plate. Okay, so right now it's not connected to anything, so we can say the two plates are both in neutral at this point. But what happens is if I connect it to a battery, let's say the positive terminal is above, the negative terminal is below. So what happens at this point is you will have a pump. Okay, essentially you have connected this capacitor here to a pump. So what will happen? You'll be moving the positive charge from a low potential to high potential. Remember, the function of the battery is to pump the positive charge from low electric potential region to high electric potential region. So the positive charge will be moved from the bottom plate, it will be moved upwards into the upper plate. Okay, so I will represent it by removing the positive charge below, and okay, so there's less positive charge below, then there's more positive charge above. Okay, there's gain of positive charge at the upper plate, there's loss of positive charge in the lower plate. Okay, so what happened? If you look at it, the upper plate has more positive charge compared to negative charge, so you can say the upper plate become positively charged, or we call it as the positive plate. So there's positive charge being stored in this plate. Okay, and if you look at the bottom plate here has only negative charge, so you can see that there's more negative charge than positive charge. So the lower plate has already become a negative plate. So the amount of charge stored in the lower plate is negatively charged. So essentially there's charge stored in this capacitor. Okay, and this is the idea of what does it mean by when we say it store charge. It means by a some amount of charge has moved from one plate to another plate. So it causes the amount of charge stored inside the capacitor to be equal to Q. Okay, so when you shift the charges from one plate, you shift it to another plate, what happens is you create a positive plate and you create a negative plate, right? And what we learned from electrostatics in chapter 1 is that if you have a parallel plate which is oppositely charged, what happens is you create an electric field in between these two plates. Okay, there's a uniform electric field formed in between these two plates, and actually this uniform electric field here means that there will be a potential difference in between these two plates. So right now, what happens? There will be a potential difference represented by symbol V in between the two plates. Again, in chapter 1, the potential difference is in the symbol of delta V, but now we enter chapter 2, the potential difference will be carried by symbol V. Okay, so this V here is not electric potential anymore. This V here is potential difference. Difference in electric potential between the positive plate and the negative plate. Okay, so again to summarize, you connect to a battery acts as a pump. It pumps positive charge from low potential region to high potential region, causing accumulation of positive charge at one plate, whereas there's loss of positive charge in another plate. The gain in positive charge in one plate causes that plate to be positively charged. The loss of positive charge in one plate causes that plate to be negatively charged. So now we can say that the capacitor is charged to a charge of Q, and the potential difference across them is represented by V. Now that we know what is Q, we know what is V, we can say that the capacitance is the ratio of the charge on each conductor to the potential difference of the between the conductors. Again, we have positive Q, we have negative Q, and in between them there's a potential difference of V. So if you take the charge stored in the capacitor divide by the potential difference between the capacitor plates, you get your capacitance, which is represented by symbol C. Okay, the symbol for capacitance is C and the unit for capacitance is farad. But usually you won't see common capacitors in our daily life to be in the unit of farad. Okay, it's actually quite rare to see capacitors in unit of in the order of farad. Usually we see it in around microfarad, or you usually see in nanofarad, which is much smaller than the farad that we are talking about. Okay, so capacitance is a scalar quantity, so it only has magnitude, it has no direction. So there's it's nonsense to talk about, oh, capacitance has a direction. No, capacitance don't have a direction. Okay, so this is a capacitor, a typical capacitor that you can find in circuit board. I actually have one here with me, so this is a capacitor. I use it from for other projects over here. You can see that the capacitor, I've already cut the leg, so I can't really show it to you. One leg will usually be shorter, one leg will usually be longer. So one of the leg, you can see that there's a gray stripe over here. Not sure if the camera can show it clearly or not. There's a gray stripe over here. So that gray stripe over here represents, you can see that there's negative sign being labeled on top. So that means that this is the negative terminal, whereas the other side, which has no label on it, will be the positive terminal. Okay, so a capacitor, usually this one, it has polarity, so you have to connect it correctly in order to charge properly. Okay, if you connect it in the wrong polarity, it might cause some serious hazard. I've seen capacitors explode just recently. Okay, so on the left here, we have a capacitor which we can see being labeled with 1000 microfarad. So this is a 1000 microfarad capacitor. You don't need to worry too much about the 25 volt being labeled here. It doesn't mean that the power supply is 25 volt. It just means that the maximum voltage that this, or maximum potential difference that this capacitor can sustain is around 25 volt. Okay, it's just a rating, a kind of label. Okay, so on your right here, you have another capacitor which is 100 microfarad. So you can see that this one has a maximum voltage of 450 volt. Okay, so on the left is 1000 microfarad capacitor. On the right, you have 100 microfarad capacitor. So since 1000 is larger than 100, we know that the capacitor on the left over here has greater ability to store charge, has greater ability to store energy, because it has a higher value or greater value of capacitance. But if we, okay, so what can we know from this capacitance here? If we connect these two capacitor, okay, this 1000 microfarad capacitor and this 100 microfarad capacitor, if we connect them to the same 10 volt battery, okay, so on my left here, I connect them to the same 10 volt battery. What happens is this battery will serve as a pump, like as we mentioned earlier. It will charge the capacitor. So at some point later in time, the capacitor will, let's say, be fully charged. So there's a certain amount of charge being stored in them. Okay, so if you wish to determine how much charge is being stored in this capacitor on the left and how much charge is being stored in this capacitor on the right, we can apply the equation that we just learned earlier, which is C is equal to Q over V, where capacitance is the ratio of the charge stored in the capacitor divided by the potential difference between the two capacitor plates. Okay, you rearrange the equation and get Q is equal to CV. Sub in your C and your V, you get that on the for the capacitor on the left, you will have a charge of 0.01 coulomb. So it means that once you fully charge this capacitor, the amount of charge that you have in this capacitor is 0.01 coulomb. Whereas the capacitor on your right over here will store an amount of charge which is 0.001 coulomb. Okay, right over here we can see that 0.01 is greater than 0.001. So what conclusion can we make? A capacitor with larger capacitance will store a greater amount of charge. Okay, greater amount of charge when you connect them to the same potential difference of power supply. Okay, So the capacitor with greater capacitance has the ability to store more charge when put under the same potential difference, whereas the capacitor with smaller capacitance has the ability to store less charge when being put under the same potential difference. Okay, I'm applying the same power supply to them, the same 10 volt power supply. So because they have the same V, the difference in the capacitance will cause a difference in the amount of charge stored in these two capacitors. Okay, so let's move on to another situation where we charge a capacitor with two different batteries. Now these two capacitors here are the same capacitor. They are identical capacitor, 1000 microfarad, 1000 microfarad. Now I connect the capacitor on the left to a 10 volt battery, whereas I connect the capacitor on the right to a 20 volt battery. So what will you think will happen? What happened to the capacitance? Well, the capacitance will actually remain constant. Okay, you might be too hung up on this equation to see that, oh, the increase in V might cause a decrease in C. So in this case, if I have a greater V, it will cause my capacitance to become a smaller value. Okay, let me write it down. You might think that C is equal to Q over V. Okay, so if you increase your V, it will cause a decrease in C. Okay, well, this idea is false. Okay, this idea is false. Okay, well, the capacitance will remain constant actually, because capacitance is actually similar like a constant of proportionality, just like the spring constant you have in F is equal to Kx. You stretch the spring more, you increase the X, but you only result in a greater restoring force F. The K will not change. The K depends only on the physical properties of the spring only, whether it's a longer spring, a shorter spring, a larger diameter spring, a smaller diameter spring. The physical properties of a spring dictates K. Okay, how much you stretch it, how much you compress it won't change the K. So when you change your X by stretching it more or stretching it less, you are only affecting the restoring force of the spring. You are doing nothing to the spring constant of the spring. Okay, bringing the idea over here, C is equal to Q over V here. C, as I said earlier, is a ratio of Q to V. So what does it mean? This ratio here should be fixed. Okay, if I have a 1000 microfarad capacitor, then it's 1000 microfarad. So if I bring it to charge with a larger battery, a 20 volt battery, what happens is I actually charge it, I actually store more charge in the capacitor. By increasing the voltage the voltage of a power supply that is connected to, what happens is you only increase the charge stored in that capacitor itself. Okay, if you try to think about it, it's actually logic. Okay, this capacitor here, if you go read it, I'm not sure whether it will appear on the camera, it reads 1000 microfarad. Okay, so now let's say I connect it this is a 9 volt battery. Okay, a 9 volt battery connect to a 1000 microfarad capacitor. Okay, then tomorrow I change it to a 20 volt battery. Does it make the reading on the printing on your capacitor change to a large smaller value? Because just now I say if I increase V, decrease C. If you have that kind of idea, that means if you connect it to a larger voltage, then it will change the printing on the capacitor to be a smaller value, which is illogical, right? It's already printed on the capacitor. How do you change the value? 1000 microfarad is 1000 microfarad. That is fixed. Okay, so the C is fixed. What change is only if you connect it to a larger voltage, what larger battery, what happens is there's more charge stored inside it. That's what changed. Okay, so I hope you have a clear idea. The C usually doesn't change. The C is a constant. If you increase V, only the Q will increase together. Okay, so what would change due to the change of V? It's the Q that would change. Initially, you will store, again, another mistake. This is microcoulomb. This is microcoulomb. Okay. Initially, you might store around 10,000 microcoulomb in this capacitor, but after that, because you change it to a larger battery, you will store double the amount of charge inside the capacitor by changing the voltage of the power supply. Okay, so C remain constant at 1000 microfarad. That's the message that I want to convey here. Okay, Next, increase in V causes increase in Q, with C being constant. So that's the main idea that we want to tell you here. Okay, so what actually decides how big is your C or how small is your C? What kind of factor actually controls C? That's the next thing that we want to study here. What affects the capacitance of a capacitor? So basically, you can split it into two main factors. One, the first factor is the dimension of the capacitor. So dimension, we talk about dimension, is a length, is a width, is a height, right? So for this capacitor here, there are two particular dimensions that you need to pay attention to. Okay, this is the first factor that control capacitance. It's the dimension of the capacitor. So when you talk about dimension, there are two things you need to be careful. First would be this area here. Okay, how wide is your capacitor plate, the area? Okay, the next thing you need to be careful about is this D over here, which is the distance between the positive plate and the negative plate of the capacitor. These two here are important dimensions of the capacitor, because by making the area of the capacitor wider, you will change the capacitance. By making the distance between the capacitor plates to be further apart, you will change the capacitance. You will need to do some adjustment to the capacitor to change the capacitance. You cannot change the capacitance by plugging it into a larger battery. That will not change anything about the capacitance. Again, to change the capacitance, you have to do something to the capacitor itself. In that case, by changing the area of the capacitor plate, or by moving the capacitor plate nearer or further away. Okay, so how does the area and the distance between the plates controls your capacitance? Well, it is represented by this equation here, where the capacitance is equals to, well, the area is actually directly proportional to the capacitance. So means larger area, larger amount, larger area, larger capacitance. But the distance between the capacitor plate actually is inversely proportional to the capacitance. So if you make the distance between the two plates to be further apart, by making them further apart, you increase the D, you actually make the capacitance to be weaker. Okay, so what's the constant that that relates between the capacitance, the area, and the distance between the two plates? Well, that constant is epsilon naught. Okay, where epsilon naught here is actually called as the permittivity of free space. Okay, so permittivity is sort of like an idea how good does it permit the electric field in between the plates. Okay, you can think of it like that. Okay, so because in between the plates here, I'm not putting anything inside here. So that's why this place here, we call it as free space. Okay, right now, currently it's free space. So how good does this free space permit your electric field? Is represented by this value here, epsilon naught. And epsilon naught is actually a constant. And if you refer to your constant sheet, it is equals to 8.85 times 10 to the power negative 12 meter per negative 3, kg per negative 1, second per power of 4, area power of 2. Well, actually, the simpler unit is just Fermi per meter. Not Fermi, Farad per meter, sorry. Okay, so it's a fixed value. So you take this fixed value that you can find in the constant sheet, multiply by the area of the capacitor plate, divide by the distance between the two plates, you get your capacitance. Okay, so what we can know from this relationship, if we increase the area, it will cause an increase in capacitance, and if you increase the distance, it will cause a decrease in the capacitor. Okay, so that's what you need to know regarding the first important factor that affects the capacitance, which is the dimension of capacitor. Okay, next you look at the presence of dielectrics. So the second way for us to manipulate the capacitance, second way for us to change the capacitance, is by replacing this free space here with something else. So it means that we insert something in between the two plates. Okay, so the thing that we insert in between the two plates, we'll call it as dielectrics. Okay, so dielectric is something that you insert in between the parallel plates. And this dielectric, okay, if you think logically, it has to be an insulator. It cannot be a conductor. Why cannot it be a conductor? Because if it's a conductor, then you cannot hold positive charge at one plate, negative charge at another plate. what happens is the positive charge will just move over and cancel out, then everything goes back to neutral. Okay, so you do not want to provide a pathway for the charge. Okay, you spend so much time, you use the battery to bring the positive charge from this terminal, you bring it out to the upper plate. Okay, you use your battery to take the effort to bring it from the lower plate to bring it to the upper plate, causing the upper plate to be positively charged. But then you insert a conductor here, then the positive charge will just drop back to the lower plate. So what's the purpose then? It's a waste of time. Okay, so you don't want a conductor to be in between the two plates. So this dielectric here must be an insulator. So this insulator is to prevent the positive charge from moving from the positive plate back to the negative plate. You already put a lot of energy to shift the positive charge from the negative plate to the positive plate. Now you put an insulator here to prevent that positive charge from dropping back into the lower plate. Okay, so that's the purpose of a dielectric. But by inserting different kind of dielectric, you can actually affect the capacitance of the capacitor. Certain material will cause the capacitance to be increased by a big amount. Certain material will cause the capacitance to change by a little bit. Okay, so we will talk about this right now. Okay, so dielectrics, okay, the thing that we insert in between the capacitor, always increase the capacitance of capacitor. So if you do not have a dielectric, the capacitance must be a lower value. Once you insert the dielectric, after that the capacitance must be a larger value. The insertion of this dielectric must always cause the capacitance to increase. Okay, so because of that, if we call the capacitance before insertion to be C0, C0 here, the naught represents before, okay, whereas after insertion you call it as C, we know that because C0 to C is always an increase, therefore we can say that C0 must always be less than C. Because you go from C0 to C, it must be an increase. Okay, so once you are clear with that, previously I already mentioned that C0 is equals to E0 A over D. But if you insert a dielectric in between, do you change the area? Well, the area is still the same area, so that's the same area. Does the distance between the two plates still changes? Well, you see initially it was this white, after that it is still that white. It's the same distance between the two plates, so it's still the same D. So what has changed right now is the permittivity. Initially here it was a free space. So free space, we know the permittivity is 8.85 times 10 to the power negative 12. But is it the same when once you insert the dielectric in between it? No. The permittivity of that space here, because you insert a different kind of material, the permittivity will change. So this permittivity here will not longer be epsilon naught. Epsilon naught is for the original case, which is without the dielectric. So epsilon naught is free space. But now it is not free space. We should not put epsilon naught. We should just put epsilon. Okay, so this epsilon here will represent the permittivity of the material. Okay, permittivity of the dielectric. The dielectric, what is its permittivity? Is represented by this symbol epsilon. If you have a knot inside, then it's not a dielectric, it's the empty space. So we call it as permittivity of free space. But once you insert it, it's no longer a free space. You have to change it to the permittivity of the dielectric. Okay, so use these three information here. C0 is equal to epsilon naught A over D. C is equal to epsilon A over D. And C0 must be smaller than C. So if C0 is smaller, then this epsilon naught A over D must be smaller. C is larger, then epsilon A over D must be larger. But we know that A and D are the same thing. So the only thing that's different is the epsilon naught and the epsilon. So we know that C is larger, that means by epsilon should be larger. So you can say that epsilon naught is less than epsilon. Or you can say the permittivity of free space is always always smaller than the permittivity of any other dielectric that you put inside the capacitor. If you insert a dielectric into the capacitor, the permittivity will definitely improve. It will get better. The permittivity will get into a larger value if you insert a dielectric in between it. Okay, so what's the relationship between the permittivity of free space and the permittivity of the dielectric? Is related by this thing called dielectric constant. Okay, so the relationship, you can express it like this, where the permittivity of the material is equals to taking the permittivity of free space, multiply it with a multiplier or a factor. You can think of it like a factor or multiplier, and this factor here we call it as dielectric constant. Okay, this epsilon r here is called dielectric constant. Another name you can think of it as relative permittivity. That's why there's r down there, relative permittivity. Okay, so you can think of this relative permittivity like what? It's like a multiplier. Okay, initially that space, the empty space, can only permit this well, 8.85 times 10 to the power negative 12. It can only permit this well. But once you insert this dielectric inside here, then we can say that, let's say this dielectric improve the permittivity by twice the amount. So in that case, we will take the permittivity of free space, multiply by 2, right? Because it improved by twice the amount. Then you get the dielectric permittivity, which is twice the amount of the permittivity of free space. So that twice here represent a multiplier, or you can say how much the permittivity improved by, right? Okay, so this epsilon r here represent how much does the permittivity improve by how many times. Okay, so if you refer to this table on the left here, which sometimes other books use kappa, but here we use epsilon r. Okay, different material possess different value for epsilon r. Okay, so if you put air in between the parallel plates, you actually improve the permittivity by 1.00059 times of the original permittivity, which is when it's vacuum. Okay, if you put in mica, let's say mica in between the capacitor, so what happens is you improve the permittivity by 3 to 6 times of its original permittivity, which is 8.85 times 10 to the power negative 12. If you insert benzene, it improved by 2.28 times. So this improved by how many times is represented by this epsilon r here, which is the relative permittivity. Means by comparing, or with respect, comparing to the free space permittivity, or with respect to the free space permittivity, how many times does it improve relative to the free space permittivity? That's why I call it as relative permittivity. Compared to the free space permittivity, how many times does it improve by? That's why we call it as relative. Okay, or you can call it as dielectric constant. Simple. Okay, certain books use the symbol of kappa for dielectric constant or relative permittivity, but in our syllabus we will use epsilon r in this case. Okay, so it's a simple calculation. Take the free space permittivity, multiply by how many times does it improve, then you get the permittivity of the dielectric itself. Okay, we know that it always improves, it never make it worse. Okay, insert a dielectric never makes the permittivity gets worse, it can only improve it. So improve means by epsilon here will always be larger than epsilon naught. So because epsilon is larger than epsilon naught, we know that if we take epsilon divide by epsilon naught, you always be a value larger than 1. Okay, so because larger than 1, we can know that epsilon is always larger than 1, which is what we can see all over here. All these values are always larger than 1 because it can only improve the permittivity compared to the permittivity of free space. You never make it worse than the permittivity of free space. Okay, so that's the idea that we want to carry from here. So now, because we know this relationship over here, where epsilon is equals to epsilon r multiplied by epsilon naught, we can replace this epsilon, this permittivity of dielectric over here, we can replace it with epsilon r, epsilon naught. So now this equation will be equals to epsilon, not sure whether I can change color or not. So this will be epsilon r epsilon naught. We have already replaced this epsilon over here with epsilon r epsilon naught a over d. Okay, whereas for the one which is vacuum, it will still be the same thing. Okay, so from here, if we do a comparison, we'll see that epsilon naught a over d here is actually just c naught that we can see on the left, right? So we can combine these two equations here and form a conclusion which says that c naught is actually epsilon r. It's actually epsilon r multiplied by c naught. Okay, so by saying that the permittivity improved by this much, we can also say that the capacitance improved by this same amount. Okay, let's say epsilon r is 2, means by the capacitance improved twice, then it becomes twice the original capacitance after you insert the dielectric. Okay, so the same epsilon r here represents the relationship between the capacitance before insertion of dielectric and after insertion of dielectric. So this epsilon r here is a very important value, and different material with different value of epsilon r. Okay, so to recall what have we learned until this point, we can say that for parallel plate capacitor, the capacitance is affected by two things. First, the dimension of the capacitor. So if you have greater, wider area, you have greater capacitance. If you have a narrower gap in between these two capacitor plates, you have a smaller d, you increase your capacitance as well. Okay, if this space here is not filled with anything, it's a vacuum, then the permittivity of vacuum is just represented by this value epsilon naught 8.85 times 10 to the power negative 12. So that's what we know regarding the first factor, the dimension of the capacitor. Next, we should also consider whether we insert anything in between the plates. So anything that we insert in between the plates, we call it as dielectrics. And dielectrics always increase the capacitance because epsilon r is always greater than 1. Why see PowerPoint? Well, there's no PowerPoint for you to see this time. I'd like to remove it. Come on, cooperate. Okay, so we know that C is equals to epsilon A over D, and because we know that epsilon is equals to epsilon R epsilon naught, okay, so we can use these two information here and find our conclusion, which says that by inserting a dielectric of dielectric constant epsilon r, you improve the capacitance by a certain factor epsilon r. So you can take the original capacitance without insertion of dielectric, multiply by the dielectric constant, then you get the capacitance after insertion of dielectric. So that's the purpose of this dielectric here, is to improve the permittivity and as a result improve the capacitance of the capacitor. Okay, so we learned about the two factors. So these two factors plays an important role in changing the capacitance of a capacitor. Okay, so in the next part, we are going to continue and discuss if we increase the capacitance by inserting a dielectric, we increase the capacitance, but the increase in capacitance, does it cause an increase in your charge or it causes a decrease in your potential difference between the plate? We know that C must increase, but this increase in C, does it relate to the increase in Q, or does it relates to the decrease of V? Which one is correct? And we'll see that it's a case by case thing, and we'll discuss further about this in the next part of the video.